Hello students, in this video we are continuing with the concept energy of a fluid in a steady flow. Energy, you know energy, different types of energy are there. You have steady flow, you already know what is steady flow. The velocity at a particular point should be constant. Velocity at different points can differ, no problem in that, and that kind of fluid which is going to have steady flow or streamlined flow, that is called an ideal fluid. That is one of the condition. Second, it is not compressible, incompressible, it is irrotational and no viscosity, zero viscosity. So we are taking an ideal fluid. Now what we are going to do here is we are going to find out what is the energy per unit volume. Okay. Now what is the energy of the liquid per unit volume? So let us find out what are all the energies possible. I have drawn here a cylinder and there is a narrow pipe here, and now what are the energies it is going to possess the moment there is a piston here. It is a movable piston, right? And if there is a piston here, you know the weight of this liquid will apply a sideways pressure and this will move this side. Okay, so there are three energies are going to be there. One is kinetic energy, and another is potential energy, and another is pressure energy. The sideways pressure it is exerting, it is called pressure energy. We will find out what are these three energies per unit volume, because we need to keep something constant. Here we are keeping volume as a constant per particular volume, maybe 1 liter, maybe 20 liter of that volume. Okay. Now what is the formula for kinetic energy? Kinetic energy is equal to half mv square. It's very simple, right? Let me write this side and later I will derive one by one. Okay. Half mv square. Now what is the kinetic energy per unit volume? That is equal to half mv square upon capital V. That is equal to mass upon volume. Mass upon volume is what? Density. So half into rho v square. This is kinetic energy per unit volume. We call this as equation number 1. Next, we move to pressure, potential energy. Okay, we will keep pressure energy here. This is the first one. Second point is potential energy. What is the potential energy? Gravitational potential energy, which is due to the height of the liquid column, which is equal to mgh. Okay, this is a normal formula. Now we want potential energy per unit volume, that is equal to mgh upon capital V. Once again, mass upon volume is equal to density, so rho g h. This is potential energy per unit volume. We will call this as equation number 2. So what we have done, we have calculated two factors here. One is kinetic energy due to the flow of liquid, the flow movement, and second is potential energy due to its position or height of the liquid, because again we are talking about fluid dynamics. The water is flowing through the pipe here. That's what we are studying. You remember we studied also the equation of continuity. Area into velocity is a constant. We did this also. These are all to do with fluid dynamics. So let me erase this part here and take only the result. Kinetic energy per unit volume is equal to half rho v square. Similarly, potential energy per unit volume is equal to rho g h. Okay, now our last point is that we want to calculate the pressure energy. Now, pressure energy is nothing but work done. Energy and work are two sides of the same coin. You do work, Because you have energy. When work is done, that means energy is being supplied. Now, we need to calculate in terms of work done. What is the work done? Work done is equal to force into displacement. Now, what is the displacement? What is displacing? The liquid is applying a pressure, sideway pressure, right? And the piston is moving from here to here. The distance traveled by that is x. So, multiply by x. We are talking about pressure. So, how do we connect pressure with force? We know pressure is equal to force upon area, or force is equal to pressure into area. The area of the piston I have taken is small a. So, I will make a change here, P into small a. So, let me put it here, P into small a into x, that is equal to, right? So, what is area into distance? Area can be written as L into B, right? And the x is nothing but distance, length, height, LBH. So, instead of A into X, I can substitute volume. So, I have here P into V, right? So, this is what I have got here. That is pressure energy, W is equal to F into X, force into displacement. And for force, I substituted from here. Pressure is equal to force upon area. And then P into V. This I have got as work done. Now, work done in terms of pressure. So, this pressure energy is equal to here what? Pressure energy, PRE, per unit volume is equal to, this we have to consider here, pressure per unit volume is equal to P into V. Okay, pressure upon unit volume we have taken. So, we have to consider the volume here. Volume is here we have. So, F into X, P into A into X, right? Pressure is this much. Okay, fine. P into V. Just let me cross check little bit. I have a doubt here, right? Pressure energy is P into V. See, I have again made 10-15 pages notes. So, I thought pressure, I checked that one. I checked it, it is P into V. Yeah, that is pressure energy we calculated. Pressure energy, yes, fine. Now, these are the three things are there. Let me remove all these parts now. Fine. Okay. See, there is a liquid. Again, an ideal fluid, non-viscous, non-rotational, steady flow and density, that is incompressible. So, with this liquid which is moving, so this is the energy we got. So, what is the total energy? We can write here total energy is equal to kinetic energy plus potential energy plus pressure energy. Okay, kinetic energy is half rho V square plus rho G H plus, just let me cross check a point here, that will be better for me. Yes, rho G H. Yeah, this is where I had a doubt. Per unit volume, so let me divide by V. V gets cancelled. So, pressure energy is just only P. So, P is the pressure energy, right? Unit volume we are talking. That's why that V got cancelled. I had a small doubt on this matter. Okay, so that's why I cross-checked it. Okay, so total energy of the fluid in a steady flow, it consists of three energies. Kinetic energy, half mv square, I substituted per unit volume, I got density. Potential energy, mgh, again per unit volume, I substituted V and it became rho. Here I calculated force multiplied by distance and all that I did it, and pressure, PV, I got it, PV upon V you do P. And this total energy of the liquid flowing in a uniform or varying cross-sectional tube is a constant. Suppose I take a a tube, let us say, like this, let us say, right? Varying cross section. Okay, it should have varying cross section. Let me draw a little bit carefully. Just a minute. Yeah, I can take a varying cross section. Let me take uniform cross section. Yes, like this and like this. So, if suppose I have a piston here, I push the water will be moving in this direction. I am applying energy to push it. This is variable area of cross section. This area of cross section is A1 and A2. A1 is greater than A2. You will find that the energy, the kinetic energy, the potential energy due to the surface, and the pressure energy which is pushing this, all of them will remain constant for, this remains a constant for a fluid, which is ideal fluid, This relationship is called Bernoulli's theorem. Dear students, you will be studying a wonderful theorem, Bernoulli's theorem. Bernoulli, let me write the name here, Bernoulli's theorem. Okay, what does this theorem says? For an ideal liquid, when the flow is through a tube of varying cross section or uniform cross section, whatever it is, the total energy is conserved. It is based on the law of conservation of energy. The liquid is flowing through from here to here with varying cross section, or even it can be same cross section, doesn't matter. Only small factors will get changed. Then you will find that the total energy inside that liquid due to its flow will remain constant, and that is called Bernoulli's theorem. When I showed another video, full video for only Bernoulli's theorem, here my aim was to just introduce the three types of energy and what you say about how do you connect the three types of energy and how that energy is remaining constant, and that turns to Bernoulli's theorem. I hope you understand what I have done. There is one extension, yes, and that extension also I would like to do it in this particular video. Okay, so everything remains same. Again, discussion is about energy only. Fine. Let me erase this part now. Okay. Okay. There is a strange terms. We call it, one is called velocity head, and second is called potential head. Okay, and third one is called pressure head. Okay, these are the three terms. What these three heads are, these are useful for you to do the numericals, otherwise they are very simple. See, you know kinetic energy, we solved that it is half mv square. We said that per unit volume. You don't do here for unit volume, we are going to do it for unit weight. What is weight actually? Weight is mass into gravity, mg. We are going to do for unit weight. Unit volume, that leads you to Bernoulli's theorem directly. Now this, you can use it maybe kinetic energy per unit mass, that is equal to half m v square upon m. Mass gets cancelled, so you have half v square. The kinetic energy per unit weight, that is equal to half v square. Mass already got cancelled, so instead of weight you have only one factor, that is g. See, mass is m. When I add g here and I put g here, I have weight. Okay, this is equal to kinetic energy per weight, which is equal to, you can say, half V square upon G or V square upon 2G. And this is called velocity head. You will use it in numericals. Otherwise, I am not sure of how it happens to be used. Kinetic energy head or velocity head. Okay, what is velocity head? Value, that is kinetic energy per unit weight. That means it depends on the weight of the liquid, not on the volume. You know, volume is only space occupied. Weight is mass into gravity, right? So velocity head is V square upon 2G, right? This is one thing, right? 2G. Next is, I am going to remove this. I am going to discuss about potential head. Okay, potential. Okay, don't go to potential head. Potential energy is equal to mgh. Potential energy per mass is mgh upon m. Potential energy per unit weight, that is potential energy plus weight, is equal to mgh upon m into g. G is come over here. mg gets cancelled. That is h, and that is called potential head. Potential head depends only on the height of the liquid. So I will write here potential head is equal to h. Okay, dear students, numerically you can apply all of them, and applications are there. They are also very interesting. That we will do it later. Right, now last I come to pressure head. Okay, pressure head. Pressure, what is pressure head? Again, force into displacement we did, all that we derived it, and we said that pressure energy, that is pressure energy PV. Okay, this PV, which we are going to say for the equation which we solved, was force into displacement. Let me solve it. Okay, from there I will derive it. How to derive this potential head? Force is pressure into area into x, that is pressure into volume. Okay, this we have got it now, pressure into volume. Fine. Now pressure head is going to be, pressure head is pressure upon volume. Okay, so again not volume, mass, that is equal to P into V upon M. Pressure upon mass, V upon M. What is V upon M? M upon V is density, and V upon M reciprocal, 1 upon rho. 1 upon rho, reciprocal of it, right? So I can put here P upon rho. Okay, now I want with the pressure head is nothing but with respect to the weight, pressure with respect to the weight, or pressure energy with respect to the weight. So I got a G here, I put a G here. So I will write here pressure head is equal to, right, P upon rho G, rho into G. So these are the different ways we are studying the liquid fluid dynamics. There we are going to have energy we studied, and we got an equation, and we moved to Bernoulli's theorem from there, and then I defined these factors: velocity head, potential head, and pressure head. So these are the three words you use it: head, head, and head here. Okay, velocity, here you got velocity. Potential is nothing with respect to height, and pressure with the pressure, and you got all the factors which you need. So there are three heads are there which we are going to use it. I hope you understand what I have done in this whole derivation. Just as you are learning some things new, right? See, when you take middle school physics 6th to 8th, you don't learn so much, right? If you're in ICSE board, you learn a lot. And when you come to 9th and 10th standard, again in CBSE level, you learn a very little, right? In ICSE again, you learn more. And when you come to 11th and 12th standard, in CBSE and ICSE both, they have the equal syllabus, same syllabus, approximate 95% is same, but the question paper of CBSE is more tuned to entrance examination like IIT and NEET examination, JEE main. The paper will be more, we will say, concept based with a lot of numerical, and the trend is different in the case of. That's why these things we need to do. It is not just for your home examinations, it is not also for the competitive examination. So today I have tried to do certain equations for you. You also try some numerical, because video shooting of numerical, after I complete this syllabus of theory part, then I will shoot videos for numericals also. So I hope you understand what I have done. In the next video, I will derive the equation of Bernoulli's theorem, which I showed you already, and then other videos will be for its applications, right? Thank you so much. As usual, if you have any doubts, please message me. I'll be able to answer you back, right? Thank you so much.